Hi everyone, welcome back or welcome for the first time to Math TV with Professor V. In this video, we're going to go over descriptive methods in regression and correlation, chapter 14 for introductory statistics. And to start off, we're going to cover section 14.1 on linear equations with one independent variable. So linear regression and correlation are two commonly used methods for examining the relationship between quantitative, remember, numerically valued variables, and for making predictions. And to understand linear regression, we're first going to review linear equations with one independent variable. Some of you might have seen this topic in algebra classes a few times, but we're just going to refresh so that we're ready to look at linear regression. So y-intercept and slope. For a linear equation in the form y equals b naught or b sub 0 plus b1x, the number b0 is called the y-intercept and the number b1 is called the slope. Now this is probably different for most of you because when you're taught how to write the equation of a line in slope-intercept form in algebra, you've probably seen y equals mx plus b, where m is the slope and b here is the y-intercept, right? So now for statistics, we kind of switch things around. It's basically the same thing as had we written b plus mx. So notice they're putting the y-intercept first and then the slope times the line. And we're changing up the variables names here, okay? So we're using b naught or b sub 0, that's the y-intercept, and then b sub 1, that's your slope. No more m. Just for stats, okay? I'm sorry if you hate it. Anyways, so what does the slope do? The slope tells us the steepness of the line. It's rise over run. You might even remember the formula for how to compute the slope of a line given 2 points. You're not going to need any of that in this class. Basically, just think of it this way. If the slope is positive, then the line, if you're looking at it from left to right, is slanting upwards, okay? Or basically, if you're walking on it, you're walking uphill. Hey, look at me going uphill. If the slope is negative, then the line is sloping downwards. And we always look in terms of x increasing from left to right. So it's going downwards here. Oop. And then lastly, if the slope is equal to 0, then the line is horizontal, constant, flat, like you're on the treadmill and you set the incline to 0, flat road. Okay, now when we're looking at linear equations, and all equations specifically, the independent variable is the variable that can be controlled or manipulated. And in this case, that will refer to x. X is your input, that's the independent variable. And then the dependent variable is the variable that cannot be controlled. Its value depends, that's why it's dependent, on the corresponding value of the independent variable. And that for our purposes is going to be y, okay? Good. So we're just going to go over a couple of examples for graphing lines. And in your homework, you're going to click points and graph them online on my stat lab. It's not hard to do, but I'll just do some by hand right now. So for each equation, find the y-intercept and slope, and then determine whether the line slopes upward, slopes downward, or is horizontal without graphing. And then lastly, use 2 points to graph the equation. Okay, so first for number 1, we have the equation y equals 3 plus 4x. So the way it's written, remember, the y-intercept is the constant or the number that's all by itself. So the y-intercept is right there, 3. The slope is always the number or the constant being multiplied by x. So in that case, that's going to be 4. Okay, so y-intercept is 3 and the slope is 4. To get used to using their notation, b naught equals 3. Remember, that's the y-intercept, and b1 equals 4. All right, now without graphing, can you tell which way the line is going to slope? Upward, downward, or horizontal? Well, how would you figure that out? You would look at the slope, Since the slope is a positive number, then that means the line is sloping upward. Okay, and then lastly, we're going to use 2 points to graph the equation. So if you remember how to graph using the y-intercept and the slope from your algebra classes, you can do that. Or I'll show you something else if you haven't had algebra in a long time. So we know the y-intercept is equal to 3. That tells me wherever the line is going to cross the y-axis, right? So we have the equation y equals 3 plus 4x. If I plug in 0 for x, then that means y is 3, since that's the y-intercept. Or you could just redo that in your head, right? Put a 0 in here, 4 times 0, 0, add 3. And then all you need when you're graphing a line is 2 points. 2 points uniquely determine a line. So pick any other x value. What do you feel like? How about 1? And if I plug in 1 for x, 4 times 1 is 4, 3 plus 4, that's 7. Alternatively, you could have used the slope. I'll show you, but we don't need to get into it that intensely in this class. Here's the x-axis, here's the y-axis, 0, 3, and then the other point is 1, 7. So I'm going to go, here's 1 on the x-axis, up 1, 2, 3, 4, 5, 6, 7. That's where I'm going to plot it. Okay, and there's our line. I want it perfect. Let's redo. Oh, much nicer. Okay, put arrows on the ends because it extends forever. All right, good. Let's look at another example. Oh, if you did remember, since the slope is 4, which is the same as 4 over 1, then for those of you who like remember your algebra pretty well and would rather do it this way, that's rise over run. So once you have the y-intercept at 0, 3, you can just count rise 4, so rise up 2, 3, 4, and then run 1 in the positive direction. Okay, that's how you could get the second point. Okay, next example, example 2, we have y equals negative 0.75x minus 5. So this time they switched the order of the terms. Notice the slope here is negative 0.75 and the y-intercept is negative 5. So I'm going to write it in terms of B0 and B1 just to get you used to it, since that's what the book's going to do. So B1 is negative 0.75 and B0 is negative 5. Okay, so in this case, which way is the line sloping? Upward, downward, or is it horizontal? This one slopes downward. How do we know? Because the slope is negative. Okay, good. And then let's go ahead and graph. So I have the y-intercept, that's negative 5. So 0, negative 5 is a point. And then it's up to you to come up with any other point. And I don't like graphing decimals. I don't know about you. When you're doing your homework online, you can click to move the points and type in the coordinates. I can show you how later. But one thing I do like to do, negative 0.75, that's negative 3/4, right? Negative 3/4 x minus 5. You don't have to do this, but if I plug in 4 for x, then the fraction part's going to cancel out, because negative 3/4 times 4 minus 5, that's going to be negative 3 minus 5, so negative 8. So I'd like to graph these 2 points if you don't mind. So we have 0, negative 5, 1, 2, 3, 4, 5 here. And then 4, negative 8 would be right here. And there's my line. Okie dokie. Good. And then let's look at one more. Y equals negative 3. And you might say, but where's the x? I know, it's not there. So just, you could think of it that there's a plus 0x, if that helps you. Okay. So for part A, the y-intercept, it's still the constant, right? That's not being multiplied by x. So 0, negative 3, or just negative 3. And the slope is the constant being multiplied by x. In this case, the slope is 0. Okay, so you could say b0 is -3 and b1, the slope is 0. Ooh. So which way is the line sloping? Upward, downward, or is it horizontal? This one is horizontal. And then how do you graph it? Well, we do have the y-intercept. The y-intercept is 0, -3. And the line is horizontal. So it's just going to go through 0, -3, and it's flat. If you wanted another point, just think of what the equation's telling you. The equation has no x in it, right? It's just saying y equals -3. That means x can be anything. So x can be 0, y is -3. X could be 5, y is -3. X could be -2, y is -3. 1, 2, 3, 4, 5. See, here's 5, -3. Here's -2, -3. So when x is missing from the equation, it means you have a horizontal line, and it also means that for any value of x, y stays the same. It's -3. Okay, good. That's it. Let me hop into StatCrunch right now and just show you how to graph the lines. It's not that bad, but if you've never done it before, I want to break it down for you. Okay, so I wanted to show you how to do the graphing problems in case you've never done it online. Given below is a linear equation, y equals 2.5x minus 2. So find the y-intercept and the slope. So the y-intercept is -2, and the slope is 2.5. The line slopes downward, upward, or horizontal. We'll look at the slope. The slope is 2.5. It's positive. So that means the line's going to slope upward. Because the slope is positive. Yes, we know. And then last thing is you're going to graph the line. So you click here, and you're going to select the line tool. Later, if you take more math classes, you could graph a parabola, circle, all sorts of stuff. And if you notice up here, it'll show you the coordinates of wherever your mouse is hovering over, okay? So we're just gonna click 2 points, and that'll graph the line for us. Y-intercept was -2, so let's start with that. And then I'm noticing, oh, they're scaling by halves because they know we have that 2.5 for the slope. So you can count with the slope, like up 2.5 over 1, or you can just plug in some other number for x. So 2.5, if I multiply, say I pick x as 2 because I just don't want to deal with decimals, right? So 2.5 times 2 is going to be 5, minus 2 is 3. So 2, 3 should be on the graph. 2, 3, right there. Okay. And you can, after you click it, you can move it. But here we go. Excellent. Yes, we are. Okay, here's another example. The two most commonly used scales for measuring temperature are the Fahrenheit and Celsius scales. If you let y denote the Fahrenheit temperature and x denote Celsius temperature, okay, so y is Fahrenheit, x is Celsius, you can express the relationship between those two scales with the linear equation y equals 32 plus 1.8 times x. So determine b0 and b1. So they want the y-intercept and the slope. So the y-intercept b0, that's 32, the constant that's just being added, and b1, that's the slope, so that's 1.8. All right, good. Here's b0, here's b1. Find the Fahrenheit temperatures corresponding to the Celsius temperatures of -40 degrees, 0 degrees, 20 degrees, and 100 degrees. Ooh, okay. So here we go. They want the Fahrenheit temperatures, which is y. So y is 32 plus 1.8 times -40. So 32 plus 1.8 times -40, that gives you -40. And this is degrees Fahrenheit. Oh, so that's interesting. -40 degrees Celsius is equal to -40 degrees Fahrenheit. They intersect there. Okay, what about 0 degrees? So y equals 32 plus 1.8 times 0. I don't usually put units in the equation, just the number when I'm plugging in. This is going to be 32 degrees Fahrenheit. 20. Y equals 32 plus 1.8 times 20. I did this earlier, but I'm double checking. 68 degrees Fahrenheit, and then lastly 100. Y equals 32 plus 1.8 times 100. Yes, 212 degrees Fahrenheit. Okay. Then in the next part, they ask us to graph the linear equation y equals 32 plus 1.8x using the 4 points in part B. So let's list them out as ordered pairs. It'll probably be easier. So remember, all of these values here that I inputted for x were Celsius, and then the corresponding Fahrenheit values are y. So I'm going to write out ordered pairs. We have -40, -40. We have 0, 32. Remember, it's always x comma y. We have 20, 68, and then 100, 212. If I'm being honest, I'm probably not going to graph that last one, okay, guys, because I don't feel like scaling that wildly. So here's x, here's y. If I scale by 20s, if this is 20, 40, 60, 80, 100, then this would be -20, -40, -60, 80, -100. I'll scale my y-axis by 20s as well. So 20, 40, 60, 80, 100, but then 212, it's going to be off the charts. 120, 140, 160, 180, am I going to do it? 200, and then that would be 220. I don't know. We'll see. We'll see how our mood takes us once we get there. And then we do have -40. Okay. Yada, yada, yada. So -40, that's right here. 0, 32, should be somewhere around here. 20, 68, and then 100, 212. Oh my goodness. Am I doing it? Am I doing it? Maybe somewhere around here. Hopefully they all line up beautifully. Oh wow, okay. Look at us. We did graph them all. Okay. D. Apply the graph obtained in part C to estimate visually the Fahrenheit temperature, so the y value, corresponding to a Celsius temperature of 28 degrees. Okay, so look at it. If x is 28, so here's 20, here's 40, so 28 would be somewhere in here. What would y be? 28 maybe is somewhere around here. So what would y be? I'm going to guess 85. How's that sound? I don't know. Then calculate that temperature exactly by using the linear equation. Okay, so y equals 32 plus 1.8 times 28. And if you put that in the calculator, let's see. 1.8 times 28 plus 32, 82.4 degrees Fahrenheit. So we were off, but obviously we were just eyeballing it, not too bad. I do want to give you my trick that I love using when I travel, because where I live we use Fahrenheit, but if I go to Europe or most other places in the world, they use Celsius, right? So the equation's 32 plus 1.8 times x. This is your Fahrenheit temperature. This gives you the Celsius temperature. You're supposed to multiply by 1.8 and then add 32. What I do instead is I double it. So in my head, just to get a rough idea, you know what I mean? In my head, I do 2x instead of 1.8x. So obviously I'm overshooting my estimate, but then I only add 30 instead of 32. And it's not perfect, you guys, but it'll give me like a ballpark idea. Like for example, that last one of 28 degrees Celsius. So using my approximation, I would have done 2 times 28, so that's 56. 56 plus 30, that's 86. You know, so yeah, I'm going to be off. It was really 82.4, but at least, you know, 28 degrees Celsius, when I hear that, it means nothing to me. I'm so sorry. But at least if I hear that the temperature's in the 80s Fahrenheit, I have an idea of what it's going to be like. So feel free to use it if you like it. It's a crude approximation, but it'll tell me if I need a jacket for the day or not. Okay, enough about that. Let's get back into statistics. So now that we've reviewed graphing lines sufficiently, we can go into studying the regression equation. And real life applications are rarely as simple as that Fahrenheit and Celsius example that we just looked at, where one variable can be predicted exactly in terms of another variable, right? There's no guesswork. There is a set formulaic relationship between Celsius and Fahrenheit, but most of the time when we're studying two variables, it's not going to be so spot on like that. So let me give you an example. For instance, suppose an educator wants to see how the number of absences for a student in their class affects the student's final grade. So the data obtained from a sample are shown here. So for their privacy, names have been removed for the students. The students are just A, B, C, D, E, F. X, the independent variable, is counting how many times they were absent. What is student B doing? Going to the beach every other day? And then here's their final grade, Y, okay, out of 100. 70, 65, 96, 94, 75, 82. So for the data set above, a scatter plot, which we've done before, would be the best way to provide a visual representation of the relationship between the variables. So a scatter plot is a graph of data from two quantitative, numerically valued, remember, variables of a population. And in a scatter plot, we use the horizontal axis for the observation of one variable and a vertical axis for the observation of the other variable, usually X horizontally, right? And then Y vertically. Each pair observation is then plotted as a point. So you can see here, I've made a scatter plot for absences versus final grade. And right now what we were looking at was linear relationships between two variables. So say you're trying to approximate or figure out a line that we could use to approximate the relationship between absences and final grades. That looks like a good one, right? It doesn't go through all the points perfectly, but it goes through a lot of them. Should we say that that line, the equation of that line, is the one that represents the relationship? Or maybe, it went through this guy and it was off on everybody else. Should I try to go through more points? Would this one be a better line? Or what do you think? Maybe something more like this? Is that a better line? How do you know? So in statistics, we're going to figure out which line best fits the data points. And the criterion that we use to determine which line is the best one to fit your scatter plot is the least squares criterion, okay? And that's the line that has the sum, the smallest possible sum of squared errors. Why are we squaring the errors? Well, I have an example for you to show why that is. Okay, so first one here, below are two linear equations and a set of data points. So line A has the equation y equals 9 minus 2x, and line B is y equals 6 minus x. And then here's the data points. Here's what we would have from our sample. It just represents nothing right now, okay? Plot the data points and the first linear equation on one graph, and then the data points and the second linear equation on the other. Okay, so I'm gonna only draw the first quadrant because everything's positive, right? Look at x and y. Yes. So I'll say this is x, this is y. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7. Okay, so I'm gonna plot the scatter plot first. these ordered pairs are 1, 8, 3, 0, 4, 3, and 4, 1. Got it? Okay, so 1, 8 is here, 3, 0 is here, 4, 3 would be here, and then this is 4, 1. And then now they want me to graph it on the same axes in the same first quadrant with line A and then separately with line B. So what I'm going to do, I'm going to copy this over here. Okay, and then we'll graph line A on this one and line B over here. Okay. So let's look at line A. I'm going to write the equation. Y equals 9 minus 2x, and then line B is y equals 6 minus x. So the y-intercept is 9. That means it crosses the y-axis at 9. So there. Slope is -2, -2 over 1. So get another point. 1, 7 is another point on that line. And also I know the x-intercept is 4.5. You don't need to worry about that, but I just like graphing with intercepts. Okay, so there's line A. Line B, 6 minus x. So y-intercept is 6. Also, if you plug in a 6 for x, y comes out to be 0. So here's line B. Okay, which one would you say fits the data better? Well, we're going to use the least squares criterion to determine, okay? You're not just going to eyeball it. We're going to construct a table now to find the error. And we define error to be y minus y hat and the error squared for each of the lines. And then find the sum of those two columns. So let me show you what's going on. You're like, why is there this y hat? Okay, y is the value from the scatter plot, okay? Y hat is the predicted value from each of the lines. So this is from the line, not an actual observed value, okay? So here we're going to make a little table. I'm going to have x, y. Y hat is what the line is telling me, okay? And then let me write out y hat, the equation of the line. So for line A, it's 9 minus 2x. And then we'll have the error and then the error squared. Okay. I feel like that was crooked. Okay, and then we want a line going down. I'm constructing a table by hand. Bear with. There we go. Am I happy? I think I'm as happy as I can be. And then I'm going to do it once for line A and then once more for line B. So line B's equation was 6 minus x. Okay, so here, this one's for line A and this one's for line B. When you do this in your homework, it's easy because they already have the table for you. You just punch in the values. Okay. Let me remind you what the values were from the scatter plot. So x and y, I'm just going to transpose these. It's 1, 8, 3, 0, 4, 3, 4, 1. So 1, 8, 3, 0, 4, 3, 4, 1. And then again, same thing here. 1, 8, 3, 0, 4, 3, 4, 1. Okay. Then what I'm going to do is find all of the values at those x's that the line would have predicted. So what I'm going to do is plug in, for example, 1 for x. So this would be 9 minus 2 times 1, so 7. 9 minus 2 times 3, 9 minus 6, so that's 3. 9 minus 2 times 4, 9 minus 8, so that's 1. And then this one's the same. And then error is equal to y minus y hat. So y minus y hat is going to be for this first column, for this first row, 8 minus 7, that's 1. 0 minus 3, that's -3. 3 minus 1, that's 2. And then 1 minus 1 is 0. So these are all the errors. Look, you could see it here. I want it to make sense to you. This is error, right? There's 1. This is error, -3. No, that one's not -3. Excuse me. This one's -3. This is error. This is error of 2. And then this one's actually on the line, so that's why the error is 0 right there. Okay. If you add up all the errors, 1 plus -3 plus 2 plus 0, if you add them all up, you get 0. So we get 0 not because the line perfectly goes through all the points, but because it worked out so that when the line was overestimating the predicted values, right? When we had positive error, it ended up canceling out with the negative error. But that doesn't mean, oh, the line went through everything so beautifully, the sum of the errors was 0. So that's why we square the error. I don't know if you remember, we did this with standard deviation too. We square the error. So 1 squared is 1, 3 squared is 9, 2 squared is 4, 0 squared is 0, just so that the negatives and positives don't cancel each other out. And then we're going to sum up the error squared. So 1 plus 9 plus 4 plus 0, that's 14. Okay. Now we're going to do the same thing with line B. So let's figure out all of the y hat values. So these would be, in this case, 6 minus x, so 6 minus 1, that's 5. 6 minus 3 is 3. 6 minus 4 is 2. And then again, 6 minus 4 is 2. Then the error is y minus y hat. So you're going to do 8 minus 5, that's 3. And then you'll do 0 minus 3, that's -3. 3 minus 2, 1. 1 minus 2, -1. Okay. Again, notice if we sum up this column here, the errors, it's set up so that the positive and the negative errors end up canceling each other out. Again, not because, oh, the line is so great, it goes through everything perfectly, there's no error. No. So let's square them all. So the positives and negatives don't cancel out. And 9 plus 9 plus 1 plus 1 is 20. Ooh, okay. So determine which line fits the set of data points better according to the least squares criterion. So least squares criterion tells us that the line of best fit is the one that has the smallest sum of the squared error from these residuals. We'll talk about what a residual is in a minute. Basically, it's that error. And the one that minimizes that is line A. Is that what you had guessed or no? Did you guess that when I graphed it? Be honest. Okay. Now, obviously, we're going to have more complicated data sets, and we're going to use StatCrunch to help us figure out what the line of best fit is. So this takes us into now the regression line. The regression line is the line that best fits a set of data points according to the least squares criterion. It is used to see trends in data and to make predictions. It is important to note, though, that computing a regression line and using it to make predictions when x and y do not have a significant linear relationship, which we'll explore in the next chapter, is useless. And you do really need to be careful with this, because the computer or StatCrunch or whatever technology you use, if you give it a set of data points and say, hey, find me a regression line, it will. But that doesn't mean that it's meaningful, especially if your data is all crazy and it doesn't look linear. Like you might have data that's parabolic in nature, right? And oh, it'll go ahead and give you a regression line, but it wasn't appropriate, okay? So you have to make sure you use this method appropriately. Regression equation is the equation of the regression line. So here's the format for writing the regression equation. Right here, I'll rewrite it. Y hat equals B naught plus B1x. Why do we use this little y hat? Because we want to differentiate between the actual scatter plot values, the observed values, x, y. That one's observed, no hat on it. That's from the data, from the sample, versus y hat, that's from the regression line, what it predicts that y should be, okay? And then here's the formula. I included it here in the notes, but you're not going to have to learn it, know how to do it by hand or anything. We're going to use technology. So just keep in mind, though, the criterion for finding a regression line. Before you find the regression line for a set of data points, draw a scatter plot. There's going to be some exercises in the homework where you practice this. They'll give you the scatter plot, or you can just go in to StatCrunch, have it make one for you, okay? And if the data points do not appear to be scattered about a line, do not determine a regression line, all right? And then here is that example that I showed you earlier of the teacher collecting the data on 6 students, their absences versus their final grade. The scatter plot is shown, and then in Excel, actually, I went in and got the equation of the regression line. Notice it's sloping downward. We'll talk about what that means. And then the y-intercept is 96.784. So let's hop into StatCrunch right now. I want to show you a couple other examples of how to find the equation of the regression line in there so you can get through your homework. All right, so let's get into doing some regression. This is question 14. Use the given data set to answer parts A and B. A says find the regression equation for the data points. So there's only 5 of them, but we're going to put that data in StatCrunch. And then you're going to go to Stat, Regression, and Simple Linear. Then you have to tell StatCrunch which variable is x, which is y. In this case, they're just called x and y, but later you'll see the names will matter. We can also do a hypothesis test and confidence interval, but that's for later on. So just leave it alone. You don't have to click anything else, and then hit compute. So here is our little printout. Okay, up here, parameter estimate. So that's the y-intercept, 8.4, and then here's the slope, negative 2.2. So you're going to type that in. So y-intercept 8.4, and then I'm just going to put minus, since the slope is negative, 2.2x. Well done. Then they want us to graph the regression equation and the data point. So you just have to pick which graph is correct. One thing I'm going to point out, look at the slope. The slope is negative 2.2. So the line should be sloping downward, downward. This one's upward, upward. So no, it's either A or B. And then what we want to look at is which set of points matches better and the y-intercept. Here's the y-intercept. It's 8.4. This one looks like it's crossing the y-axis up there. This one's way too low. It's going through 0, 0. So I don't even need to waste my time thinking about it anymore. Okay, move on to the next question. This one's more spicy. So a random sample of 50 cities have the data on average high and low temperatures in January shown in the accompanying table. Use the technology of your choice and the given data to complete parts A through F. Use high temperature as the explanatory. So explanatory is X. Here's the table of data values. You guys, this is when you're so grateful for StatCrunch. You really think you're going to sit there and enter this all in Excel or your graphing calculator? No, thank you. So open it there. And we're done with this. First part, it says obtain a scatter plot for the data. Choose the correct scatter plot below. So we're going to go graph scatter plot. X variable, that's explanatory. They said use the high temperature for X. Y is low, and then hit compute. So it's sloping upward. There's like a little gap in the middle, and then another clump up here. Which one looks like that? It's B. Okay. Next part. Decide whether finding a regression line for the data is reasonable. So is there a linear pattern? Yeah, it looks like there's a linear relationship. It's sloping upward. So I would say, yeah, it is appropriate to carry out regression. So there is a linear pattern. No, not inappropriate. There is a linear pattern, so it is appropriate. There's not a curved. Okay. So I'm going with B. Okay. Determine and interpret the regression equation for the data. Select the correct choice below. Okay, so here now we're going to go stat, regression, simple linear. X variable is high temperatures, Y variable is low. That's it. And then click compute. And here they're telling us to round to 3 decimal places. There's the y-intercept, there's the slope. So the regression is, and then is there either a negative or a positive linear relationship? Well, look at the slope. The slope's positive. So I'm going to enter my answer on B because there's a positive relationship. They want the y-intercept first. So negative 7.579. And then the slope is 0.906. Okay. Are there any outliers? Let's look at the scatter plot. Was anybody sticking out like a sore thumb? No, I mean, there was a clump that was separated from the main bunch. Maybe this guy's kind of out there, but I mean, outlier would be way, way far away from everybody. I'm going to say there aren't any. Okay. There are no outliers and no influential observations. Yeah, let's just go with that. Nobody's bothering me. In case a potential outlier is present, remove it and discuss the effect. No, we're not doing that. Well done. In case a potential influential no, there wasn't. Nobody's hanging out. Okay, next question. So just to show you this one too. Oh, let me redo it. Here we have data for personal income per capita and per capita beer consumption. So here's the table, and they want us to use income as the explanatory. So let's open this in StatCrunch and get the scatter plot. So graph scatter plot. Income is explanatory. Beer consumption is going to be the y variable. And here it is. Okay, so which little graph looks like that? Oh, I didn't mean to close the StatCrunch. StatCrunch, come back to me. Here you are. Okay, which scatter plot looks like that? This one, right? Okay. So is it appropriate to find a regression line? This does not look linear. This looks like almost parabolic, but really it's just like a clump of points. So I would say there is no clear pattern, so it's inappropriate. Inappropriate, people. Check. Nice. So then the rest of the problem is, this is going to be your favorite problem in the homework set. You just keep clicking not applicable all the way through. Okay. So if you run into one, not applicable, where you can't do the linear regression, you're just going to keep clicking. This question is not applicable. All right. Enough of that. I mean, I'm just going to keep clicking it. So we're done. Okay, so let's get into 14.3, the coefficient of determination. So now we've figured out the equation of the regression line. We have all our data, and we're going to look at how good of a job is this regression line doing. So for a given x value, a residual, and you've probably heard me say that word before earlier in the lecture, that's the difference between the observed y value and the predicted y hat value. So earlier in the homework, when you were in 14.2, they just called E error y minus y hat, if you remember, but really that term should be residual. A residual is called positive when the observed value is greater than the predicted value, and it's called negative when the observed value is less than the predicted value. So here again is the scatter plot and regression line for absences versus final grade for a sample of students. So notice here, this error, this difference, doesn't look so big, but it's big. Right here, the difference from the observed to the predicted value, right? The observed value in this case is greater than the predicted value. So this is a positive residual. And then here, this one is a little bit below the predicted value, so this one would be a negative residual. Honestly, this line's doing a pretty good job, right? Okay, now recall that the regression line is the best fit for the data, meaning that it minimizes the sum of the squared of the residuals. And we can also use the regression equation to make predictions. So I could say, hey, if a student missed 7 classes, how many absences, or what would their grade be? Or alternatively, something beyond here, if a student missed 16 classes, what would their grade be? If a student missed 3 classes, what would their grade be? Etc. But we do want to make sure we're doing this appropriately and carefully. How valuable are such predictions? Well, one method that we can use to evaluate the utility or usefulness of a regression equation is to determine the percentage of variation in the observed values of the response, the dependent variable, that is explained by the regression or the predictor, the independent variable. So before you get all confused, I got a diagram. I'll talk you through it using regular language, okay? We want to look at how much variation there is between the values, which we've studied variance before. We always compare the values to the mean, okay? So that's what we have plotted here. We have the mean of all the observations. So you've got a scatter plot going on. There's the mean, horizontal line right here. Dashed horizontal line is the mean. We have a regression line right here. This is the regression line. And then we're only going to focus on one little point from the scatter plot, one little data point. It's sitting right here, okay? And I'm going to compare it to the regression equation as well as to the mean of all of the values that I collected in my sample, in my data set, okay? So notice here, the observed true value of y is up there. The regression equation predicted y hat would be here. So we've got some error. This is my residual. This is my error. That error is the deviation that is not explained by the regression. Okay, for some reason we were off and the regression equation is not accounting for it. Now there's another error here, or deviation. It's not error. It's deviation from the mean that the regression equation did account for. This is explained by the regression equation. So this deviation, obviously we don't, here's the mean, horizontal line. Most of the time, all your data values aren't going to be right here. You have some variance, you have some deviation. And whatever the difference is from the mean to the regression line is capturing the relationship or the deviation between x and y. But whatever's between the regression line and the actual observed value, your residual, is not explained by the regression. And then this quantity right here, this is all of the deviation from the y value to the mean. So notice it's broken up of 2 parts. This part right here is explained, not explained by the regression, and then this part here is explained by the regression. And we want to compare what proportion is not explained by the regression compared to the total variation. So now we're going to introduce some new terminology, okay? So the total variation is the sum of y minus y bar, so that would be the mean of all the observed values squared. So that's the sum of the squares of the vertical distances that each point is from the mean. This total variation is often referred to as SST, the total sum of squares. Okay, I know it should be TSS, but whatever. This can be broken up into 2 parts. So like we showed earlier in that diagram, there's the unexplained variation. That's the sum of y minus y prime. Some books we're using y hat. Let me put little hats on these guys. That's the sum of the squared residuals. This variation is called unexplained because it's due to chance or something that we haven't observed. This is abbreviated as SSR, sum of the squared residuals. That one makes sense to me. Okay, SSR. Then we have the explained variation. So that's the sum of y hat minus y bar squared. So that's the amount of total variation that can be attributed to the relationship between x and y. That as x changes, y also changes in some manner. It is the amount of variation that is explained by the regression line. So the regression line says, yes, we know as x changes, y is going to change. This is how it should be. SSE, okay? That's the error of the sum of squares. So the total variation, SST, is the sum of unexplained and explained variation. So you could switch these little guys to hats. Okay, and then here's the terminology per your textbook, okay? And now let's get into the regression identity, which we had basically up here. It's just instead of using sigma notation, now we're going to use the abbreviations. So the total sum of squares, SST, is equal to sum of the square residuals or regression sum of squares plus the error sum of squares. So SSE. Good. Now, why do we have this? Well, the coefficient of determination, r squared, gives you the proportion of variance in the observed values that can be explained by the regression line. So this is your total variation, right, from the mean of all the observed values. This much is accounted for by the regression line. So if I take their ratio, now I have the proportion of variation that the regression line says, yep, I knew that was going to happen. I got you. I predicted it as such. And the remaining percentage of variation is due to unexplained factors. This percentage, written in decimal form, is called the coefficient of non-determination. So if you're asked to find the coefficient of non-determination, it's 1 minus r squared, and the coefficient of determination is just r squared. Okay? So let's go through some facts about this coefficient of determination. It's a statistical measure of how well the regression line approximates the observed data points. You can think of r squared as the percent of the data that is linked or explained by the regression line. And r squared will vary from 0 to 1. R squared implies that the regression line is a perfect fit. So the regression line would go through every single data value that you had in your scatter plot. So let's look at this example here. Again, absences versus final grade, and explain the meaning of the coefficients of determination and non-determination for the regression model of number of absences and final grades, given that r squared equals 0.962. So where did I get this from? No, I didn't sit there and compute it by hand. Again, when you find a regression equation using technology, a lot of the time it will give you the value of r squared. So the coefficient of determination is r squared, that's 0.962. And the coefficient of non-determination is 1 minus r squared, so 1 minus 0.962, which is 0.038. So what does that tell me? For this regression model, we found that 96.2% of the variation in final grades can be explained by the variation in the number of absences, while 3.8% of the total variation is due to chance or other factors that we can't observe, okay? And so that's actually pretty excellent. If your r squared value is that high, it's a great, great linear relationship. Okay, moving on, last section in this chapter is section 14.4, linear correlation. So statisticians use the correlation coefficient, we'll learn what it is, to measure the strength of the relationship between two variables. There are several types of correlation coefficients, but we will focus on the Pearson product moment correlation coefficient. It's abbreviated PPMC, named for the statistician Carl Pearson. The value of the PPMC computed from sample data measures the strength as well as the direction of a linear relationship between two variables. So just to get through some notation, and then we'll talk about what direction means. R, lowercase r, is the symbol for a sample correlation coefficient. And rho, that's a Greek letter, rho is how you pronounce it. Or sometimes capital R, depends on your book, is the symbol for a population correlation coefficient. And the value of the correlation coefficient varies from -1 to 1. Okay. So here's basically a little number line that shows all the values that R can take on between -1 and 1. If your R value is -1, that means you have a strong negative linear relationship between the two variables. What's an example of a strong negative linear relationship? It's two quantities that are inversely related. So if you think about it like number of absences and your grade in the class, which we've been looking at so much, as absences go up, grade goes down, and vice versa. So those have a negative or inverse relationship. If your value of R, the correlation coefficient, is 0, that means there's no linear relationship between the two variables. It doesn't mean that they're not related, just maybe not linearly. Maybe they have a quadratic, parabolic relationship, logarithmic, etc. So it's just not linear. And then if R comes out to be +1, then you have a strong positive linear relationship. So for example, the number of hours you worked, and assuming you're not on salary, your paycheck, right? As you work more, your paycheck should go up. As you work less, your paycheck will go down. Unless you got a salary job, then so sorry. Okay, so R can take on any value between -1 and +1. If it's closer to either -1 or +1, then it's stronger, okay? Here's the formula. Again, don't worry about it. We're not gonna use it. We're gonna use technology to help us in this day and age. It's your job to interpret it and know what it means and know what it represents, not sit there and just crunch it out. So just some facts I wanna reiterate. R measures the strength of a linear relationship between two variables. And so the following properties of R are going to be meaningful only when the data points are scattered about a line. First, R reflects the slope of the scatter plot. So the linear correlation coefficient is positive when the scatter plot shows a positive slope and is negative when the scatter plot shows a negative slope. The magnitude or absolute value of R indicates the strength of the linear relationship. So a value of R that's close to -1 or +1 indicates a strong linear relationship between the variables. And then we could say that the variable X is a good linear predictor of the variable Y. If you have a value of R near 0, then it indicates at most a weak linear relationship between the variables. And the sign of the correlation coefficient R and the sign of the slope of the regression line will always be the same, okay? So both should be positive or both should be negative. So I'm gonna show you different scatter plots and what the value of R is for each, okay? So notice here, this first one, the points all perfectly lie on the regression line. So that's why we say we have a perfect positive linear correlation. It's positive because they're sloping upward. In example B, still very strong. Almost all the points are on the line, but it's not perfect. So this is strong positive linear correlation. R is 0.9 for this data set, okay? Oh my goodness, look at C. It's a hot mess. I mean, if you take the line out of there, you're like, it's just a blob of points, right? This is a weak, it is positive because it's somewhat going upward, right? But it is not good. R is 0.4, weak positive linear correlation. Like, would you want to use that line to predict where the points are going to be? No, thank you. Okay, here's an R value of -1. Again, see how all of the points in the scatter plot lie perfectly on the regression line? So this is a perfect negative linear correlation. So -1, perfect negative, +1, perfect positive. This is a strong negative linear correlation. R is negative 0.9. Yeah, almost all the points lie on this negative sloping line. Here is a weak negative linear correlation. See how the trend is downward here, but I mean, what is this? And then here, last one, example G, no linear correlation. It is just a blob. You can't even say that they're like kind of going up or kind of going down, right? It's just a hot mess. So who knows what that data set represented. Okay, we're going to get into StatCrunch in just a second, but I did want to talk about one last idea, correlation and causation. So it is important to note that generally speaking, correlation does not imply causation. And you really need to be careful about this because it's a trap that many people fall into thinking. Two variables might be strongly correlated because they're both associated with other variables called lurking variables that actually are the ones that are causing the changes in the two variables under consideration. So let me give you some examples. A study showed that teachers' salaries and the dollar amount of liquor sales are positively linearly correlated. It doesn't mean, though, that liquor sales going up means teachers' salaries are going to go up, or teacher salaries going up is what's causing liquor sales to go up. A possible explanation for this fact might be that both of the variables are tied to other variables, such as the rate of inflation, that pull them along together. Also, another one I like is a study, this is true, showed that BMW owners, those who own BMWs, and life expectancy are positively linearly correlated. So it doesn't mean, hey, I want to live longer, let me go out and get a BMW for myself. There's a strong linear correlation between those two variables. No, but if you think about it, people who buy luxury cars like BMWs, they probably have access to better health care, maybe better nutrition, all sorts of things that would enable them to have a longer life expectancy. So just because there's a correlation between two variables doesn't mean that one of them causes the other one to behave that way, okay? All right, now let's get into StatCrunch, and we're done with chapter 14. Okay, so let's look at some of the homework exercises for 14.3. In this question, it says, a study on the relationship between the estradiol levels of pregnant women and the birth weights of their children is given in the table. Here, X denotes estradiol level in milligrams per 24 hours, and Y denotes birth weight in hectograms. Use the information to complete parts A through D. So A says, decide whether finding a regression line for the data is reasonable. And then if so, continue. So to decide, we want to just first make a scatter plot and see, is there a linear relationship between the two variables? Does it look like they have some sort of linear graph? So graph, scatter plot, and then X is X, Y is Y. And let's just see what it looks like. It's sloping upwards. It's not the best, but I'd say okay. So there is a linear pattern. Let's try. Excellent. Okay, continuing. It's not the best one though. Compute the coefficient of determination R squared. Select the correct choice below. So now we're going to go to stat regression, simple linear, and then select your variable. So X is X, Y is Y. That's all you have to click. And then compute. And then up here is your value of R squared. Okay, 0.5221. That's the correlation coefficient rounded to 4 decimal places. 0.5221. Well done. Continue. Determine the percentage of variation in the observed values of the response variable explained by the regression and interpret your answer. So remember, the coefficient of determination, r squared, tells me how much percentage of variation is attributed to the regression equation. So this is going to be 52.21%. Just take r squared, make it a percent. Okay. So now we're going to assess how useful the regression equation is. Is it not useful, moderately, or very useful? And D doesn't make sense because we did do linear regression here. I'd say it's moderately useful. It's not fabulous. We've had better. 52%, half of it, you know. I'm going with that one. Okay, so that's all you're going to have to really do for regression. Then I wanted to hop over, and now we're in 14.4. These are all pretty easy. Here we go, 21. So let's do this one again. So the following are the age in years and price in hundreds of dollars for a certain type of car. A scatter plot of the data is given to the right. Okay, so if you want to look at it, they already have it for us. Here's all the data points. Okay. Obtain the linear correlation coefficient. So that's R. So I'm going to take the data, open it in StatCrunch. And I'm going to go stat, regression, simple linear, and then X is age, Y is price, and I'm trying to find the value of R. That's my linear correlation coefficient. They even put it right here, correlation coefficient. So this we're going to round to 3 decimal places. It's negative 0.951. Well done. There is, what would you say? A strong negative linear association, little to no linear, a strong positive, a weak negative, a weak positive. Well, the value of R, remember, matches the slope of our regression equation. So R is negative. There's a negative relationship between the variables. 0.9 is very close to 1, so that's strong. A strong negative linear association. Fantastic. So the given graph is consistent or not consistent? It's consistent, right? That graph matches with the interpretation that we found in part B. Remember, when you have a negative relationship between two variables, that's the same as them being inversely related. So one goes up, the other one goes down. And we can say because the y values appear to decrease as the x values increase, yeah, they go opposite ways, and the data points appear, what would you say, essentially scattered about a horizontal line? No. Clustered closely about the regression line. That sounds good. I didn't graph the regression line, but if I did, they would be close. Or widely scattered. No, this was a strong relationship. So they're going to be close to that regression line. So let's check. We're so good. So that's pretty much it. And then the rest, oh yeah, I don't need points. I'm demonstrating. Same idea. You can see this one's a lot more wild though, right? Just for you guys to explore the different options. And then this one's looking good. Can you guess what the sign of R would be? See how this one's sloping upward? Okay, so that's the end of chapter 14. In the next chapter, now we're going to look at hypothesis testing to determine how useful our regression equation is. So stay tuned. Subscribe if you haven't already, Math TV with Professor V, and give this video a thumbs up if you found it helpful.